Irodov problem number 1.74. In the arrangement shown in the figure, the mass of the rod capital M exceeds the mass small m of the ball. The ball has an opening permitting it to slide along the thread with some friction. The mass of the pulley and the friction in its axle are negligible. At the initial moment, the ball was located opposite the lower end of the rod. When set free, both bodies began moving with constant accelerations. Find the friction force between the ball and the thread if t seconds after the beginning of motion, the ball got opposite the upper end of the rod. The rod length is equal to L. Let's draw the diagram. Okay, so this is our diagram. Now, the key thing here is this particular ball is not attached to the thread. The thread just passes through it, and there is some friction between the thread and the opening in the ball. So, first thing you need to realize is this is not held by tension in the rope. Okay, so we will look into that a little closely. On the other side, it's pretty simple. So we have a big mass M, so it will exert some force, there should be some tension, and what would happen is the big mass M is accelerating downward with acceleration A, okay, and the small m is accelerating upward with acceleration A dashed. Why did I say it is not accelerating with the same acceleration A? Because there is an additional thing happening here. There is some friction between the mass and the string. So that will have some effect on the net acceleration. If there was no friction, if the tension was responsible for pulling the mass up, then A dashed will be equal to A because it's a continuous string. Okay. So let's start with drawing the free body diagrams for big M and small m. So for big M it is simple. We can draw the force due to gravity and then tension, and this is accelerating downward with A. Okay. Now for this small m, I'll do a couple of things. Let's suppose this is the small body M and the string is passing through it. The tension in the string is not holding this ball. The tension is not responsible, it's not acting on the ball. There are other forces acting on the ball. So let's draw all the forces acting on M. What are the forces acting? Number one is of course gravity, mg, and then the thread is moving up. The ball is trying to move down. Okay, so relative to the thread, what is the motion of this ball? It is downward. Now let's try to find out which direction the friction force acts. The other force that is acting is friction, but which direction the friction force acts? Now friction always opposes relative motion. So relative motion of ball with respect to string. Okay, so the string is going up, the ball is going down. Relative to the string, the ball is going down. Okay, so if the relative motion of the ball with respect to string is downward, the force of friction will be upward. So kinetic friction, always remember, it is in opposite direction to relative motion. Okay. Okay. Now I also want to draw what the forces are acting on the string. Forces acting on string. Now there is tension in the string, which is same as this. The string exerts a force of friction on F on the ball. By Newton's third law, the ball will exert an equal and opposite force of friction on the string. So there will be a force of friction F working in this direction. Okay. So make sure that you understand this part. This is critical. What are the forces acting on the small mass m? The force of gravity and friction in the upward direction. Tension is not acting on the small mass m. On the string there is tension, and due to Newton's third law, equal and opposite forces will act on the string. So if the string exerts F on m, m will exert minus F on string. Okay. Now that we have the free body diagrams, one other thing. And we said this ball is accelerating upward with acceleration a dashed. Okay. Okay. So now that we have the free body diagrams, we can write the equations of motion. So mg minus t is equal to ma. From here we can write F, which is this way, minus mg is equal to ma dashed. And here the string is massless, so T has to be equal to F. Okay. So from here we can find A. A is mg minus T by m. Now T is same as F, so F we can write A as mg minus small f by friction force by m. Okay. From here we can write A dashed is equal to F minus mg by m. So we got A and A dashed. Now relative acceleration of small m with respect to big M will be what? Will be A plus A dashed. Okay. Time taken to cover distance L is t, and this is both A and A dashed. It is given in the question that they are constant accelerations. So we can use the equation S equals ut plus half at square. Okay. So S is the total distance covered. Initial velocity was 0. Half at square. Total acceleration is A plus A dashed, and it covers that distance in t square. Okay. Now let's substitute the values of A and A dashed. So 2L equals mg minus f by m plus f minus small mg by m. So 2L mm equals mmg minus mf plus capital MF minus capital mmg. This and this we can cancel. So F m minus m is 2L m. Or F we can write as 2L. Oh, wait a minute. Where did the t square go? Two L m by m minus m t square. Or we can maybe write this little bit neatly as 2L by t square mm by m minus m. Okay. So So that is our force of friction acting on small m.